Good morning, students. Today I would be taking a next graph traversal algorithm, that is your DFS. In previous lecture, I had discussed BFS, breadth first search, and now I'm going to discuss with you depth first search. Okay, so we have already done this BFS, and I had told you what's the meaning of breadth first search. Okay, and the time complexity I had discussed, and this was the algorithm. Okay. Next is your depth first search. The concept of this and how to do this depth first search, that is similar to your breadth first search, but the only difference is that instead of queue you have to use a stack. So if you are using a stack, then you will be traversing all the nodes depth wise. Okay, so here I have taken that example. Suppose this is your graph and you have to traverse this depth wise using the depth first search. Okay, so again I need to take one node as the source node. It can be anything, it can be B, it can be E, F, C, but here I have taken A. Suppose A is my source node. So in BFS what we had done, okay, we had inserted the source node in a queue, but instead of queue here I would insert that in a stack. Okay, so I would be inserting that in a stack. All other steps are going to remain same. Okay, in BFS I had taken the visited array. Here also you need to take the visited array. So I would be making over here 1 2 3 4 5 6. So many nodes are there? 6 nodes. So here it is 1 2 3 4 5, and I'm taking this 6. Okay, suppose this is your visited array and this is the visited array element A. This one is your B, this is your C, this one is your D, E, and F. Okay, so here I'm writing. So first of all, the visited of all the nodes, that is your 0. So I'm here writing 0. So here I'm writing 0. Okay, so what is the first step? You have to start from the source node, push that into this stack A. So A would be pushed. Once you have pushed that, the visited of that would be set to 1. So here I'm making this as 1. Okay, now next step was that pop the element, pop A from the queue, print it. So I'm printing it over here. Then all the nodes connected to A. So what are the nodes connected to A? You have B and C. You have to push them into the stack, but before pushing, what you have to check? What is the visited of them? What is the visited of them? Already 0, so I can push them. Now I have pushing first C and then B, but it can be B or C. In any order you can push them, that doesn't matter. Okay, so this visited of now, because I have pushed B and C, visited of B and C would be set to your 1. Okay, now pop the topmost element from the stack. Okay, what is the topmost element of the stack? This is B. So pop this B, print this B. Okay, now all the nodes connected to B, check those. Only two nodes are there, A and D. But the visited of A is already set to 1, so I won't push it again. What is the visited of D? That is 0. So I can push that into the stack. So push that into a stack and visited of that would be set to your 1 now. Okay. Now this is now printed. D is printed. Okay. Delete this D. Pop this D. Print this. Then all the nodes connected to D. All the nodes connected to D were B and F. What is the visited of B? It is already 1. So what is a visited of F? 0. So I have to push that into the stack. So push that into a stack and visited of that would be set to your 1. Okay. Next, pop the next element from the stack. F. Print this one. Okay. All the nodes connected to F, you have D and E. Now what is the visited of D? That is already 1. So I won't consider this. What is the visited of E? Okay. This was actually E. This was F. Okay. You assume that this is your E. This was your F. Okay. So what is the visited of E? That is 0. So I will make it 1. Okay. And E would be pushed into the stack. E is pushed now. Now I have to pop the next element from the stack. What is the next element? Topmost element E. Pop this, print this one. All the nodes connected to E, check those, F and C. Okay. Now what is F? F is already 1. What is C? C is already 1. So I won't consider these. Okay. Once this is popped, what is the topmost element of the stack? C. Pop this, print this one, and all the nodes connected to C, A and E. But the visited of A and E is already 1. Okay. So now what is stack? Stack is your empty. So this is your output of the DFS. Now just check this. How it is visiting, traversing this graph. First A, okay, then B, then is your D. So depth wise we are going. After A, B, then D. After B we are not visiting C. Okay. So A, B, D, then F. Okay. So after F you are coming up like E and then you are coming to this C. So this is your depth first search. If I will implement this graph for DFS, output would be like this: A, B, C, D, E, and then F. But here it is different. Okay. So now again I'm repeating this algorithm. What we have done. First I am taking this graph. In that graph, the visited of all the nodes would be set to 0, and I have to take one stack. First step is that you have to push the source node into the stack. Next, you have to delete the element, you have to print this, and all the nodes connected to this you have to check, B and C. And B and C you will push into the stack only if the visited of them is your 0. If the visited of them is 1, you won't push that element into the stack. Next, all things are going to remain same. Pop the topmost element, print it, just check all the nodes connected to this. If the visited is 0, push that into the stack like this way, and you have to do this procedure until your stack is empty. Once your stack is empty, this is the output of your DFS. Okay. So the method is similar to that one of BFS. Only difference is that instead of queue, you are using a stack. So you need to take some more example. You can find out more example from the net and try out BFS and the DFS of those graphs, because these are very important. And okay, this is the algorithm. This algorithm is similar to the one that we had done in BFS. Only difference is that instead of queue, I have used the word here stack. Okay. So what is G? G is a graph and SRC is the source node. I'm using some another variable because I need to take as a stack. So I'm taking as a stack. First was what was the first step? I had pushed A like source node into the stack. Okay. So here also push that s dot push src, or you can write down push src into the stack. Then what we had done, mark this as visited. Okay. Next, while stack is not empty, while this here stack is not empty, what we are doing, we are popping. You have to pop the element, print it, then all the elements connected to this node you have to take. If the visited of them is 0, push them into the stack. So same thing, pop the element. Suppose the popped element is your V, then for all the neighbors W of V, if W is not visited, you have to push that into the stack and mark this as visited. Okay. So here also like if you want, once you are popping, here you write down one more line, that print V, because you have to take the output also. So once you are popping, print here V. So one more thing you can write down, print V. Otherwise all these things are same. So again I am repeating, you are taking the source node, push that into the stack, mark that as visited, and while stack is not empty, pop the element, check all the neighbors of this. If they are not visited, push them into the stack and mark them as visited. Okay. Once your stack is empty, this is the traversal. This print V output that you are getting, that is the traversal of this. Okay. Okay, next we are having the applications of DFS. Applications of DFS is that it can be used for the detection of cycle in a graph. The way I have told you in BFS that both BFS and DFS can be used to detect cycle in a graph. Then is pathfinding. Pathfinding means suppose this graph is given to you and you are asked to find out, is there any path between E and F? Yes, there is a path between E and F. Okay, and suppose if I have two more nodes I'm making in this graph. G I'm taking and I'm taking suppose H. Okay, now this is a one graph. In that graph, how many nodes are there? 6 and 7 and 8. 8 nodes are there. Now if I'm asking, is there any way to go from A to G? No, there is no path from A to G. So for that you can use this DFS. Okay, so what you have to do, start from A. Suppose you have to find out a path from A to suppose first F. Start from A, take the DFS. So while taking the DFS, first you're getting A, then B, then D, then you're getting F. Once you're getting F, that means you can start from A and you can go to F. There is a path from A to F. Okay. Now I'm asking, start from A. Is there any path from A to G? Now apply the same DFS for this graph. Okay. Now you will start from A. You will get the output like this: A, then B, then D, F, E, and C. So G and H, G is not coming in this output. That means there is no path from A to G. Okay. And one more important thing that I can tell you over here is that if you're starting from A and you're getting the output like this is your DFS. This is your DFS. But sometimes you may be asked, DFT. What is DFT? Okay. Depth first traversal. Depth first traversal means you have to traverse each and every node. So if you're starting from A, you are able to find out that all these nodes are reachable from A, means you are getting the output like this. After that, if it is DFT, you have to start from a node, the visited of which is 0. Now obviously we have not visited G, the visited of this would be 0, visited of this would be 0. Now you can start from G and you can apply the same procedure of DFS. When you will do that, you will be getting G and H also here. So in the output, you are getting G and H. So that means you are traversing each and every node of that graph. You are getting this output as well as G and H also. Okay. So what you have to do, first start from A, apply DFS for this. Then you will check, is there any node having visited 0? Like G was having visited 0. You can start from G, apply the same procedure and take the DFS of this graph. So you will be getting the output. Okay. That is DFT, depth first traversal. Okay, we were discussing the application. So this can be used for the path finding. Then is to test if the graph is bipartite. So this application is that bipartite graph means that if you can divide your graph into two parts, that means if you can divide your nodes into two parts such that there is no edge between the nodes within the one graph. Suppose if I am taking this one, if I am able to divide this graph into two parts in such a way that all the nodes in one part, they may be connected. Suppose there are two parts, U and V. Suppose you are putting some nodes over here and some nodes over here. Okay, there may be an edge from U to V or from V to U, but there can't be any edge between the nodes of this part or between the nodes of this part. Okay, that means these two sets are disjoint sets. So that graph in which you can divide your nodes into two parts in such a way that they are making disjoint set, then those are your bipartite graph. Okay, so DFS can be used for that. Finding strongly connected components of a graph, again the same thing. Suppose here, like I had taken two more nodes, okay, G and H. What are the connected components? This I had told you. Connected components means like you assume that this is your one graph. So if you are starting from A, you are able to reach to all other elements. Okay, so this is your one connected component. But from A or B or C, you can't go to G and H. So this component is not connected to this one. Okay. So in this graph, there are two connected components. So this is another application of DFS. And then it can be used to solve the puzzles like mazes that we solve manually. That maze problems can be solved by using DFS. So just go through these applications of DFS. Okay. Next is, what are the differences between DFS and BFS? It stands for depth first search. This is breadth first search. BFS can be done with the help of queue. Okay. And DFS can be done with the help of a stack. Now in BFS, the space and time complexity is lesser as there is no need to do backtracking or backtracing. But here the time complexity will be more because we need to go back. Okay. So backtracing is there, or you can say backtracking is there. Otherwise, you can say the complexity of DFS is actually similar to that BFS. This is also big O of V plus E. Okay. Because just we are not using a queue, we are using a stack. Otherwise, all other things like the algorithm is going to remain same, because here also you are having one while loop, and BFS also you are having one while loop. Okay. So these two are very important algorithms. You need to take some more examples. Otherwise, I will give you some more examples and you just find out DFS and BFS of those algorithms and just go through these algorithms. You need to learn those.